Good morning, everybody. I hope you are not too tired, but my talk will be on a very different subject what you have heard this morning, and we don't have very much time. But my name is Harri Alles. I'm from the University of Tartu, but I have to say I have in the first time this building, and my research is going on in another building. It's an Institute of Physics. But a little bit about background, as I know that you come from Finland, and many of you are Finns, so I have to say that my first foreign trip was also to Finland, and Finnish people probably know was Olli Lounosmaa from Helsinki University of Technology. He's famous low temperature laboratory where I made my PhD, so graduating from Tartu as a laser physicist. When I went to Olli's lab, of course, I became a low temperature physicist, and after that I continued in Manchester, and after that I was invited back to Olli's lab. Olli was not in lead then, but to lead the interface group which studied helium crystals. And as you see, I came back to Estonia, my university, where I graduated only 4 years ago and spent more than 18 years abroad. But now about these previous studies, I would like to present one paper here which summarizes 25 years of studies of helium crystals. And we were happy to get this article, the picture of that article to the front page of Reviews of Modern Physics. You as journalists probably know what is front page and so on. So this is also like a highlight of my research, and it's the most cited paper of me. But at the same time, I didn't know yet that a little bit earlier, so in the end of 2004, appeared one paper. This paper was twice rejected from Nature, and then finally accepted by Science. And I checked day before yesterday, there was probably more than 10,000 citations. So this is a famous graphene paper, Novoselov game. And one interesting detail, when I was in Manchester, this address is very familiar to me. So the thing was that when I left Manchester as a postdoc in 1998, 3 years later, Henry Hall was retiring or giving the professorship, or his professorship of Henry Hall was then given by André Geim, who accepted this, and within only 3 years he put up great things, very many great things, but most successful was of course this graphene. And this, what they did, as already was told, with usual sticky tape, they isolated from graphite single atomic layers of graphite planes, which is called nowadays graphene, and which is a very active field. And this is our paper. This is maybe too technical, but this is a picture that they took this graphene sheet, and this is micrometer. So micrometer is a very small size, as you know. So human hair is 50 micrometers, so it's a 1/50 of human hair is a scale here. So made the contacts, put on the silicon oxide this, and measured electrical properties. And this is so that they applied some voltage here, and then this resistance of that graphene sheet changed a lot. So this is so-called electric field effect. But this is maybe too much in detail, but what is most understandable also to people to street, so they got Nobel Prize, especially for this, initiating these graphene studies, although this paper was marked this 2004, and not bad for a scientist to be, like, they got knighthoods like 1 or 2 years later, and this is a donation to a museum in Stockholm. So the usual sticky tape and some graphite and this graphene transistor. And the prize was given then for groundbreaking experiments regarding the two-dimensional material graphene. So, but essential thing was also that they found that this planar sheet of carbon atoms or this graphene is stable. So till their experiments, it was not really believed that such structure exists. It could make fullerenes, just, or these nanotubes here, and in graphite or in a pencil, they are all these planes together. But this was one of the nice achievements also, that they like proved that these two-dimensional crystals also exist and they are stable. And after that paper, you can see here 2004 should be somewhere there, and this paper appeared. This is publications of graphene. So it took up, this was really theoretical papers before, but experimental study and also enhanced theoretical study, of course, followed this paper. And this is 2010. I think it has been rising somewhere there, while then fullerenes is saturated, and also carbon nanotubes are saturated, and maybe it's even dropped because very many people who study carbon nanotubes are nowadays studying graphene. So only one slide is some of the extraordinary properties. So it's a very good electrical conductor and also thermal conductor, and also it's a single atomic layer, but it's very strong. If you measure the force to make this graphene like a hole into it, so this is like 200, 300 times stronger than steel. And then also it's only single atomic layer, but it's impenetrable for gases, even for helium. For helium atoms even cannot pass it or go through it. But now finally I got to the point what this topic was about, which means that graphene studies in Estonia, and they have been mainly carried out in this university, the University of Tartu. And this is first funding we got in principle 2009, so less than 4 years ago. So I got this Mobility Stop Research Grant, which means like a little bit less than €500,000, which is in Estonian standards quite proper money to put up your own research group and then start initiate some new study. And I was also wondering that this is also a ranking list, and I didn't have a single paper on graphene when I applied for this grant, and I got the grant. Also other people who were probably like well-known expert in their field were like after me, so I was wondering that this graphene is really a wonder material probably, and one of the referees also was mentioning that this topic is very hot and important. And this is some details, but this is the main task of this mobilities project, which is still going on, ending next year, but I will start in the end here. One of the tasks was also for this Estonian or Tartu's material scientists to join the international network of research groups working in this area. And I think at least in this task we have been having very good success, because immediately after this grant we applied for the EuroGRAPHENE project, or Euro course belongs. This is now going to end this summer probably. And here you see different universities participating, and from our side, Professor Jaan Aarik, who is well-known material scientist, he belongs to the 1% most cited scientists in his field, and his specialty is atomic layer deposition method, which I roughly or shortly then describe later, and other people also from Switzerland, Germany, Netherlands, and then the leader from this project is Professor Pertti Hagonen, actually, who is also from low temperature laboratory and Olle Lounasmaa student, and he was my thesis supervisor, so everything is very closely related. So he switched to nanophysics much earlier than me, like 1996 already, and I did the same like 10 years later. So I followed his steps. Another project is seventh frame project, RODIN, where I am a representative of University of Tartu, and this is led then from Chalmers, Andres Isaksson, theoretical physicist, but from Chalmers you might know, and in the end about this graphene flagship project is also led from that university, which is Jari Kinaret, Professor Jani Kinaret from the same lab. And this project is going to end in the end of September. We have the final meeting there. Then a little bit about the results. I don't want to give too many details, but some examples would be nice, I think. So our first examples also used similar technique as this future Nobelists, so use a sticky tape, and this is just optical microscope picture. You barely see here, and you see the scale is 10 micrometers, so you get very microscopic sample there. This is already electron microscope figure, scanning electron microscopy, and then this layer here, this is a background, which is very bright, and this is one layer, this is two probably, this is more nicely see. And this is some Raman spectrum, which is maybe too detailed, but this is atomic force microscope, which just by tip measures a step. So on the down here, there is graphene, and this is a substrate or silicon oxide. And if you go over the step, so there is a like less than 1 nanometer, like 0.8 nanometers a step, which is really that there is a one atomic layer, and after that there is nothing. So this is a nice straight edge there to be seen. And this is just microscopic samples, but to make larger samples like square centimeters or more, very simple method, chemical vapor deposition method have been like developed, and we use this also in Tartu. So this is very simple. You have some substrate where you want this graphene to grow, and then some carrier gas with source materials. And the substrate in this method, mostly this is just copper foil, which is then made hot 1000 degrees. Then some source which contains carbon will be guided in with carrier gas, and carrier gas in our case is argon, and we use also hydrogen, but carbon source is in methane, which is very widely used, and it's quite typical and procedure to get large area graphene. So this is just preparation. And this is our self-built in system, like 2 years already in use, and very much heavily used. Very many samples will be made. And this is now how it looks. So this is the background, which is in substrate silicon oxide, and this edge you can see. So this is a single layer graphene here. So you can see that optical is quite nice, almost the same. If you just don't have this edge here, you can't distinguish very easily that is there. But the beautiful thing is that you can rarely see the single atomic layer. Now about this atomic layer deposition, what I already called that, what in Tartu, the university, the people have been doing like more than 20 years and developed well like all this machinery needed for that, and they have very many published results. So why it's necessary then this kind of like make dielectrics on graphene? So here is some review paper, and this Game and Novoselav used this scheme. So they had silicon, which acted as a backgate, then was a silicon oxide, then was graphene, and they made the contacts on that path. But this is like just demonstrating this effect. To make really some use for transistor, you have to use top gate. So on graphene, you have to make some dielectric, and then the top gate, as it's here. And this was first time then made 2007, and this is also on silicon carbide, similar thing. But the main thing is that the proper method to be developed to get graphene covered with high-K dielectrics with very thin layers, like 10 nanometers, 5 nanometers. This is very important to get some applications to graphene. And this is what in Tartu we have been working. This is a principal scheme of atomic layer deposition, which enables to really by layer, just there are zirconium chloride here, and then water, just first zirconium chloride, then water, then again, like step by step, and layer by layer, then build up the dielectric. And this is very precise method, but it's very slow. But if very thin layer is needed, this is an excellent method and can be used also in technology. And I think it's also Intel is here. Intel is using also probably atomic layer deposition method, like in industry. This is a scheme. In Tartu, we can measure here also the growing of this dielectric layer here, and then there is this titan chloride and water, and this titan oxide layer will be grown by that. And these are some of the machinery. So this is probably some old ALD machine, but this is old, somewhat newer, and I think we have altogether 4. They are all home built, and the last one maybe 3 years ago was built. And now this is a picture. Now it's the same picture as maybe you remember earlier. So this down here there is graphene, and then there is this was substrate. Now it's covered with hafnium oxide layer, which is about 10 nanometer thick. And if you measure the same step here, you see that the distances or this step size is roughly the same, 0.8 nanometers, which means that the hafnium oxide has been growing with the same speed to the graphene, but also on the substrate, which is a very good result. And these results were already accepted like 2010, but it appeared 1 year later, so this published result. And we have also written a review on that, which was published in this book. The publisher was INTECH, maybe you know better even. And this was like autumn in 2011. So another topic is sensorics, as this graphene is only one surface only. There is nothing, like no volume. So it might be a very good sensor, and this is also what we have been some experiments carrying out. So in that case, we have just prepared substitutes contacts. So this is titanium is a very thin layer, and then mostly this is the gold contacts. And then on this ready-made contacts, so the distance between contacts is like 0.1 millimeter, very, very small. We just lift graphene on top of it, and then pass current through it and measure the resistance or resistivity. And you can see then in the atmosphere, there it's a nitrogen. In pure nitrogen, it's a saturates, and if you put in the synthetic air, which consists of nitrogen and oxygen, you see the rapid change, and it saturates out. We put nitrogen in again, so it's repeatable, and there's different percentages, and then you can fit this data nicely, and the graphene serves really as a model system, and we have just submitted this data. This is yet unpublished, and, but nevertheless. Another thing, still in the real air, it's problem with graphene that it is contaminated with water vapor, oxygen, and actually it's not so sensitive. And one way to lift the sensitivity or enhance it is to use ultraviolet light, which cleans the graphene. And this is just some general picture where this current source of graphene, when you put the light on, this yellow light here, when the light has been put on, it saturates. When the light off, then goes on, off. And then there are some pictures where is A means that there is no light, it's completely unsensitive. So here when the gas is put in, there is completely sensitive, insensitive, no reaction. Also here almost now. But when it's on the light B, so this is a big response here. And this big response also after this illumination will be like staying. And this is a master thesis result, and currently the preprint is written and will be also submitted probably. And then finally, the third thing is corrosion studies. You know that corrosion is also a very important technological thing, like your rusty cars, whatever it is. And in Estonia, here in Tartu, University of Tartu, Professor Väino Sammelsel has been developing his studies, and graphene nicely fits into these topics because it's impermeable to gases. It might be a very good protective coating. But actually it's so that this is now scanning electron microscope picture of the graphene, and you see that it's not completely homogeneous. There are like some darker spots, which means that there are more than one layer graphene. Probably there are defects. And the problem is that if you cover there with graphene some surface, for instance copper surface, so there will be defects. And these defects, corrosion products will come in. And finally, there is no much difference practically when you cover with graphene. Only in short term you can see some improvements. And here in Tartu we have just carried out studies and also submitted a paper where this looks ugly, but this is now some polymer called this polypyrrole is deposited on graphene, and it goes preferably to defects. It seals all these defect things. And there are some pictures here, and this might be complicated picture to look at, but to look at, the smaller are these peaks, the better resistance to corrosion in this substance is. And you can see that just copper foil and copper with graphene, it's almost the same, no big difference. Maybe copper with graphene is somewhat better, but if you use this material, it's covered with this polypyrrole, this peaks are much less. So this really helps in corrosion, which might be important result. And then I also like summarizing the three main directions here which are going on is this atomic layer deposition of dielectrics, sensorics, corrosion. And what I also want to point out that unlike these previous studies or presentations where it was huge amount of people involved, and so we are really starting from a small group. We have only 3 PhD projects. We have some senior researchers are acting now, so we are really trying to get our things going and running, but we are very small. But future projects, I can point out that this graphene flagship, as you might know, 2 projects which got then 10 years, 1 billion euro like financing, or at least plans for that, was announced in January, and it will probably in October will be like starting officially, and then there will be open call. We didn't just make it just in the first round to get on the board of this flagship, but we very much hope that we will be like in the coming years getting all this big international project, super project one could say, to participate there. Yes, thank you. So it's time.